And first thing we're going to talk about here is valence bond theory. And this is just another way of describing the bonding that takes place inside molecules. We've got a few different theories, and they kind of increase in complexity, and as a result they increase really in their flexibility and in their explanations. And so if we take a look at a dot structure of O2, what we see is we have all the electrons paired. We have bonding pairs, we have lone pairs. However, if we take a look at O2, we see that it has magnetic properties. It is paramagnetic. If you look at the very first picture on the first slide, you'll see a sample of liquid oxygen actually trapped between two magnetic poles, and that's because O2 is paramagnetic. So it must have unpaired electrons. Well, our Lewis dot structures couldn't really explain that. However, valence bond theory can explain this, and you'll see we often refer to valence bond theory just as VBT. So rather than describing a covalent bond as a shared electron pair, we're going to go a little bit deeper, and we're going to describe a bond as an overlap of an atomic orbital, of two atomic orbitals that are unfilled. Okay, so they usually have a single electron in them. And if we take a look at the energy of why that might happen, we can use a hydrogen molecule as an example, so H2. So here we've got a hydrogen atom and another hydrogen atom, and look at their energies. And so we see that the energy isn't too bad for the two hydrogen atoms separate, but notice as those atoms get closer and closer together and start to overlap just a little bit right here, the energy begins to drop. And remember, as energy drops, the stability is increased. So now as the atoms get closer and closer together, they reach some minimum energy here due to that overlap and sharing of those electrons between their orbitals. And so as it turns out, the distance where we have that lowest energy is the bond length. Now, if we struggle to push those atoms closer and closer together here, we see the energy go up, and this is due to the repulsions of the two nuclei. Remember, those nuclei are positively charged, and they don't want to be too close together, and so there's a balancing act between the stability gained by the sharing of those electrons, the overlap of those orbitals, and the repulsion of the nuclei, and that's where this happens right there. Now, valence bond theory is really flexible about how bonds can form. We see some different ways that it can form. We can have the overlapping of orbitals. You can have an S overlapping with a P, an S overlapping with a D, P's overlapping with D's, P's overlapping with P's, etc. Or we can even take a look at hybrids of these orbitals. We're going to look at that here in just a little bit. But a bond results from the overlap of any two atomic orbitals with a total of two electrons that can spin pair. What this also means is that we can take an empty orbital and overlap it with an orbital that has two electrons in it. And that's called a coordinate covalent bond. We're not going to worry about those just at this point, but we do need to be aware that that kind of bonding situation can occur as well. It doesn't necessarily have to be one electron from each atom. One atom can actually donate both electrons for the bond into an empty orbital from another atom. And when we take a look at how these orbitals are overlapping and where they're overlapping, the geometry of these orbitals is what determines the shape of the molecule itself. Let's look at molecule H2S. If we do the VSEPR model there, we see that we've got two bonding pairs and two lone pairs, and the VSEPR would predict an angle of about 105. Well, let's take a look at our orbital diagrams for each of our atoms here. We've got our sulfur atom there, 3s2, 3p4. We've got two lone electrons there. We've got our hydrogen with the two 1s's there, and they each have just a single electron there. So if we pair this electron up here, pair this electron up here, they'll spin pair, and we get a picture that looks something like this. So we've got our bond between the two right here, our sulfur hydrogen bond. We've got another sulfur hydrogen bond right here. We've got one of our lone pairs right there, one of our lone pairs right there in a p orbital. So that all looks good. And what we see though is that when we look at those p orbitals, we've got an angle of only about 90 degrees, which isn't very big. However, it is very close to the actual angle of about 92 degrees. Well, this is way off from Vesper. So what does that mean for us? Does that mean that Vesper is just wrong, that we shouldn't be using Vesper? Well, let's take a look at the molecule CH4 and see if we can use the same reasoning for CH4 that we did for H2S. So if we take a look at the orbital diagrams for carbon and hydrogen, we see that we've got carbon, it's got 2 lone electrons here. Hydrogen has that 1 lone electron there. And if we combine hydrogens and carbons there, well, we see that we have a lone pair here, and that corresponds to that 2s. We were able to overlap the 1s of one hydrogen with carbon p there, and we get a bond here, and we get a bond here. Well, and we're done. We cannot form another bond here or another bond here because we don't have enough electrons. So if we use the same method that we did for H2S, we can't even get the right formula for what's formed between carbon and hydrogen. Whereas with Vesper, we were able to get CH4 just fine. So what's going on here? What we're going to do to try to help explain all this is we're going to use a concept called orbital hybridization, which is a little bit of an odd concept, but it really does work. What orbital hybridization is a mathematical procedure that mathematically mixes atomic orbitals on an atom to get different molecular orbitals that will be used to bond into a molecule. And so if we look at a regular p orbital here, we see it's got 2 equally sized lobes. And if we start mixing it with an s orbital, so we turn it into a hybrid between s's and p's, we end up with a really large lobe here on one side and a small lobe on the other side. And that larger lobe here on the right allows for a greater overlap with a different orbital. And the greater the overlap between 2 orbitals, the stronger the bond and the more stable the molecule will be and the lower energy it'll be. So some things that we have to keep in mind when we're hybridizing orbitals is that the number of orbitals has to be conserved. In other words, the number of atomic orbitals that I mix together has to be the number of hybrid molecular orbitals that comes out. Also, hybrid orbitals have different combinations, each with a unique orientation in space. So we can combine an s orbital with 3 p orbitals and get 4 hybrid orbitals. We can combine an s with 2 p orbitals and get 3 orbitals, and those are going to be different from the other one. Or we can take an s and a single p and hybridize those, and those will look different than the other 2. So Vesper theory is going to help us kind of determine the type of hybrid orbitals that we need to form in order to complete our bonding. So let's look at some of these different types. We won't get to all of them in this lecture, and we'll pick up the rest of them in the following lecture. So sp3 orbitals, they are called sp3. It looks like p cubed, but we just say sp3. This is a combination of 1 s orbital and 3 p orbitals. And the resultant orbitals that we make turn out to be 109.5 degrees apart, just like we had in methane or a tetrahedral geometry. So this type of hybridization between an s and 3 p's is very common in 4 bonded carbon compounds, where you've got carbon bonded to 4 different things. If we take a look at the energies of the different orbitals here, for our atomic orbitals, we've got 2 electrons in the 2s and 2 electrons in the 2p. We're going to hybridize all 4 of those orbitals. So we're going to mix one of the s's, the 2s, with 3 of the 2p's, and we end up with 4 hybrid orbitals here that are between energies of the 2s and the 2p. And notice that we now have 4 hybrid orbitals. We have 4 electrons, and so we have single occupied hybrid orbitals here with which we can form 4 different bonds. And so we can do something like this with methane, CH3, and get our 4 bonds pointed in the right direction. So if we look at a picture here, we've got an s orbital. Here we've got our px, py, and pz. And when we mix them mathematically, which is way beyond the scope of this course, we end up with an sp3 down this corner, down this corner, and that corner of a tetrahedron. And that is mathematically where they point. These are these wave functions that make up these orbitals. They do include vectors in 3-dimensional space, and it turns out that all of these orbitals end up being 109.5 degrees apart and forming a tetrahedron. So those are sp3 hybrid orbitals, and we use those when we need to form 4 bonds to an atom. So here's a methane molecule here. We've got our 4 hybrid orbitals, each with an electron. We've got our hydrogen 1s's coming together with 1 electron, and together they form 2 electron bonds there. We can also do this with something like ammonia. Even though ammonia doesn't have 4 bonds, it does have 4 electron groups. And so it's got an electron that goes here, it combines with hydrogen, an electron here combines with hydrogen, 1 here with hydrogen, and then we've got another pair, and that pair is going to fit right in here in that sp3. Now we also have sp2 orbitals, and we use sp2 orbitals when we need to form 3 bonds. And this is the result of an s orbital mixing with 2 p orbitals. And the resultant hybrid orbitals, when we do the math and work it all out, we find that these hybrid orbitals are 120 degrees apart. Well, that's exactly what we would expect for 3 bonding groups, 120 degrees apart. And so here we have 2 of the 2 p's for carbon and the 2s, and so what we have left is we have 3 sp2 hybrid orbitals, so those guys combined to form there, and then we've got this last remaining p orbital that's unhybridized and that remains unchanged, and so it's still a little bit higher in energy than those hybrid orbitals. And so here we can take a look at our diagram here, where we've got our s orbital right here. Whoops. Our s orbital right here. We've got a px and a py. We could have used the pz, it doesn't really matter. But when we mix those together, mathematically we get a hybrid orbital that points at that corner, one that points at that corner, and one that points at that corner, and they are 120 degrees apart all the way around. Just like we would expect for something that has 3 electron groups. And the first thing that we're going to talk about is a little bit more in our sp2 hybridization. We started that a little bit in lecture 17, and we're going to continue that with lecture 18 here. And so how does sp2 hybridization work into a molecule? Well, first let's take a look and see what we've got with this type of hybridization. If we look at the orbital diagram, what we see is that carbon needs to form 3 bonding groups, but it only has 2 single electrons, and we can see that here in our orbital diagram. We've just got our electron right here and an electron right here, and so just looking at the atomic orbitals, that does not allow us to form 3 bonding groups, and so we need to hybridize those orbitals in carbon, and we're going to hybridize to form sp2 orbitals. Now, why sp2? Well, we need to form 3 bonding groups, so we need 3 hybrid orbitals. And what gives us 3 hybrid orbitals is an s orbital and 2 p's, and so that gives us 3. So when we hybridize those orbitals, we get something that looks like this. It doesn't really show the energies here, but we can see we go from these 2 of the p's and this s into 3 sp2s, and those are going to be used to form single bonds. And then what we're actually going to see is that this guy here, this unhybridized p orbital, is actually going to be used to form the second bond of a double bond. So let's take a look and see how that works. Now when orbitals overlap end to end, they form a type of bond that is called a sigma bond. And so we have that little symbol there, our little sigma. And when orbitals overlap side by side, they form what is called a pi bond. And we see our little pi symbol there as well. Now, anytime we have a single bond, it consists of a sigma bond. Anytime we have a double bond, it consists of a sigma bond and a pi bond. And that's the double bond that we think of. So a double bond is a sigma and a pi. A single is always just a sigma. If we happen to have a triple bond, which certainly happens on occasion, it's going to have a single sigma bond and two pi bonds. And it all depends on what's getting hybridized and what's available for bonding. Let's take a look at how our sigma and pi's form here. And so we've got a px and a py there, and we can see that when they overlap in a side-by-side conformation there, we actually get our overlap right in here and right in here, so that's how they come together. Or if they come end to end, we get that overlap right here, forming that sigma bond. Now we can take a look at a molecule that has all of these types of orbitals, and so this goes back to our CH2O molecule, and we've got our sigma bonds right here forming between the sp2 of carbon and the 1s of hydrogen. We've got another sp2 of carbon here and another 1s and hydrogen there, so they're overlapping to form a sigma bond. We've got a sigma bond forming between an sp2, the third sp2 of carbon there, and a p orbital on oxygen here. And so they're overlapping and forming a bond between them. And then we've got the unhybridized p orbital of carbon that was right here, and a p orbital on oxygen that also had a lone electron in them, and they're forming overlap here and forming the second part of the pi bond. So our double bond is the sigma bond and the pi bond, and then all of our other single bonds are just sigma bonds. Now if we take a look at bond rotation, we can see a difference between sigma bonds and pi bonds. Now sigma bonds act like an axle, and groups can rotate around that axle without breaking it because they can maintain their overlap even when rotating. So we can envision seeing those bonds right along in here that have the ability to rotate around without breaking that overlap right down there. Now pi bonds, on the other hand, pi bonds are fixed in space here and here, and if we were to rotate one of those carbons, we would move those pi's out of alignment of each other and the pi bond would break. And so as a result, the rotation for anything with a double bond is restricted due to that pi bond. Anything with just a sigma bond can actually rotate around in space. Here we see some examples of that. We've got our, this is just a CH4Cl2 molecule initially here, and I can rotate that around in space like this, and we get our chlorines here on the same side of the bond on the left, or here we can see we've got the chlorines on opposite sides of the bond here, and they just go around different places in space. Now if we look at something that has a pi bond with it, it doesn't work quite that well. So here we see our a similar molecule. We have C2H2Cl2, and we've got a case where we cannot rotate this bond. We've got this double bond here and here in these two molecules. These two molecules have identical formulas, C2H2Cl2, but because of the arrangement of the chlorines on the sides of that double bond, they do not have the same chemical properties. Here we see the chlorines are on the same side of the double bond, and so that actually is given its own name called cis 1,2-dichloroethene. That's not important, you don't need to know that. But here we have trans, and here we see the chlorines are on different sides of that double bond, and they can't rotate around to the other side like they could when we just had the or the carbon-carbon single bond in the previous molecule. So these two molecules, while similar, are very different. They have different structures, different properties. They actually have boiling points that are like 15 degrees apart. And so just this little tiny change in the bonding and change in the structure does affect chemical and physical properties. Let's take a look at our last main hybridization here, and this is sp hybridization. And this is most common in compounds that have a linear type geometry. Generally, we see that in molecules that have triple bonds, or if they have two double bonds connected to them. And when we have sp hybridization, we have a single s orbital and a single p orbital being hybridized, leaving two unhybridized p orbitals behind. And so if we look at just kind of a hybridization diagram here, we take the s and the p there, and we hybridize those right here to get the sp over here. So they're lower in energy than the original unhybridized p orbitals, and so we've got that kind of situation there. And we can see that we've got an S and a P. We use these orbitals in linear molecules, and the reason for that is their orientation in space. So we do have one of our SPs here pointing to the right. We've got another one pointing directly to the left, and when we put them together, we see that we've got two lobes directly 180 degrees opposite of each other, which is why we end up with SPs being used for linear geometries. And if we take a look at the hybridization diagram, we get something like this. And here's a molecule, C2H2, also called acetylene, that we have sp hybridization in, and we would guess sp because we've got this triple bond right here. Now, where does that triple bond come from? Well, we've got our sp hybrid orbitals, and so each carbon has two sp hybrid orbitals here. We've got one that's right here, one that's right here, one that's right here, one that's right here. So these outer ones are being used to overlap with the hydrogens to form that sigma bond. The two hybrid orbitals pointed at each other on the carbons are overlapping there to form a sigma bond between the two SPs. And then we've got these unhybridized Ps, and so we've got one there, one here, one here, one there, and then we've got them 90 degrees offset from each other as well. So we get a bond here and a bond here, and then we also have a bond here and a bond here. So those are our two pi's, and so the triple bond in a molecule like this is made of a sigma bond that's formed between the two hybrids, and then two pi bonds that are formed between two unhybridized p orbitals. Now, I mentioned that sp was our last primary hybridization that we have, but not the only ones that we have left. Anytime we're looking at geometries for expanded octets, if we're going to go to that 5 and 6 bonded central atoms, we've got to go beyond the s's and the p's. Now, once we get to sp3, we've used all the s's and a p available for a particular orbital, and so now we've got to bring in the d orbitals in order to go into an expanded octet hybridization. So if we have 5 electron groups, we've got to use one of those d orbitals in there, and 5 electron groups means we're going to hybridize 5 orbitals, so an s, 3 p's, and a d. So those hybrid orbitals are called sp3ds. If we're going to an octahedral arrangement, then we need an additional d orbital, and we need 2 of them now, so we have an s, 3 p's, and 2 d's, so we'll go to sp3d2. And we can look at these geometries here. We've got our sp3ds here with our 5 coordinate, and then here's our sp3d2's 6 coordinate in an octahedral arrangement. Of course, your 5 electron groups there are your trigonal bipyramidal. here's just a table of the different hybridizations, the different geometries that we predict from VSEPR theory. So we can use VSEPR to predict what kind of hybridizations we need in order to get the angles that we have. And here are some examples that we'll work out in class. We'll take a look at CO2, take a look at C2H4, and we'll also take a look at I3-. Let's take our next step in complexity as far as our bonding theories. So we've looked at VSEPR, we've looked at Lewis dot theory, we've looked at valence bond theory, and now we're going to take a look at molecular orbital theory. Now, valence bond theory has its limitations as far as how we explain where electrons go. We use hybrid orbitals to kind of help show us how things combine and where their electrons are going, but those hybrid orbitals are still essentially atomic orbitals. Now, MO theory uses the concept of a linear combination of atomic orbitals, or LCAO, and these make molecular orbitals, which is what we call MOs. Now, these MOs reside throughout the molecule and not just on a single atom. So in other words, they're delocalized around the molecule and not just sitting on a single atom. So let's take a look at our simplest molecule for MO theory, and that would be H2. Now, the bond in an H2 molecule can be viewed in MO theory by just looking at the overlap between the 1s orbitals that are on each of those hydrogen atoms. And when they overlap, they form a sigma bond. They're just overlapping in a single place. That's one of the ways we can identify a sigma bond. And so we call that a sigma 1s molecular orbital. The sigma indicates the type of bond formed, and the 1s tells us the types of bonds that are overlapping to form that orbital. Now, this is a bonding orbital because it's overlapping with similar phases as far as the wave functions. So if we look at that, we've got the 1s plus the 1s, and we've got the bonding orbital here. So really with the bonding orbital, very different from what we saw with valence bond theory, because now we've got an orbital that goes around the entire molecule and it spans all of the molecule there. And notice once again, it's a bonding interaction, which is a energy lowering interaction, a stabilizing action. And so our energy is going to go down for that bonding orbital, and we call this a sigma 1s. Now, we still need to preserve the number of orbitals in molecular orbital theory, just like we did for valence bond theory. So we only made a bonding orbital. We combined two 1s orbitals and created a bonding orbital. We're missing an orbital. Now, according to the LCAO method, one orbital, that orbital that we just saw, is derived by adding the atomic orbitals together. Well, an additional orbital can be derived by subtracting them as well. So we're going to see what that looks like. Now, this is called an anti-bonding orbital, and we're going to give that its designation sigma 1s star. So in the MO theory, anytime we see that star, that indicates an anti-bonding orbital. It's still a sigma bond made by combining 1s atomic orbitals, but here they're combined in an anti-bonding arrangement, which means that we are subtracting the two orbitals. So we have the sigma 1s minus the sigma 1s, and notice that our energy goes up. And what we see here is that that creates a node between them, and so that's called anti-bonding. So in the binding they combined, and in the anti-bonding we're actually changing the wavelength phase of one of those orbitals, and so we get an anti-bonding orbital. They can't overlap if they're out of phase. Now, because we can think of these orbitals as wave functions, because they really are, we can think of the adding or subtracting of these wave functions as the different types of interference. If we look at the 1s minus the 1s, that's like destructive interference. It's like having two waves out of phase, and that creates an antibonding molecular orbital, and it's higher in energy. If we have a 1s plus a 1s and they're in phase, then that gives us constructive interference, and they combine, and we get a bonding molecular orbital, and that's going to be lower in energy than the two atomic orbitals by themselves. Now we can combine all these things into molecular orbital diagrams, or MO diagrams, and we get something that looks like this and has a lot of different features. So we indicate our different atomic orbitals here, and because they're the same atom, they have the same energy. Now we're going to create those together. We're going to have a subtracting and an adding. So we have a bonding orbital here. We have an anti-bonding orbital here. We've got one electron in each of those orbitals, and we're just going to fill up our molecular orbitals with the electrons from our atomic orbitals. Well, we haven't changed anything. We still have our individual boxes. They can each hold 2 electrons. So I can take this 1 electron from the hydrogen atom on the left and put them in here. I can take my 1 electron from the atom on the right and put them in there, and we've got a bonding, 2 electrons in our bonding orbital. I don't have any electrons in my anti-bonding orbital, and so I end up with a single bond in my H2 molecule. So we have an H singly bonded to an H. So this is really just the introduction to this more complex thing we call molecular orbital theory. We're going to delve into that a little bit more as we start getting deeper into Chapter 7. It is difficult material, so as always, if you have any questions on anything we talked about today, please make sure you contact one of us. And one of the things we want to look at when we have our molecular orbital diagrams is bond order. And really what bond order is essentially the number of bonds that exist between 2 atoms. We've seen single bonds, double bonds, and triple bonds. They would have bond orders of 1, 2, and 3. And what we see with bond order is actually that we can have fractional bond order as well. And the reason that we can have that is because we can calculate bond order based on number of electrons that we have in our bonding MOs and the number that we have in anti-bonding MOs. And so we take the difference, so we take number of electrons in the bonding molecular orbitals minus the number of electrons we have in anti-bonding molecular orbitals, figuring that they're just going to cancel out, and we divide that by 2 so that we have 2 electrons per bond, and we get a bond order calculation there. And we can take a look at our hydrogen atom here. We saw this in lecture 19. We've got our bonding and anti-bonding molecular orbitals, the sigma 1s for bonding, sigma 1s for anti-bonding, and we've got two electrons that we've got for each of those hydrogen atoms, or 1 for each of those hydrogen atoms. So this electron is going to come down into the bonding, this electron is going to come down into the bonding, and give us 2 electrons down there. Now if we apply these values into our bond order equation, we would have 2 electrons in bonding orbitals minus 0 in anti-bonding orbitals. So we have 2 minus 0 over 2, and that would give us a bond order of 1, which is exactly what we expect for this molecule here, and we have a single bond. Now we can take a look at some other molecules here. We've got a helium atom, and when we look at helium gas, it turns out helium gas is nothing more than just individual helium atoms. Helium is not one of our diatomic molecules, and molecular orbital theory can show us why. If we look at 2 helium atoms there, they each have 2 electrons, and when we apply that into our molecular orbital diagram there, we have 2 electrons in the bonding, and we also have 2 electrons in the anti-bonding. So we have a bond and an anti-bond both formed, and anytime you have that, you're essentially going to cancel out any bonding properties. And if we do our bonding or bond order calculation here, we get our bond order BO is equal to 2 in the bonding minus 2 in the anti-bonding over 2, so we have 0 over 2, and we get a bond order of 0. And as molecular orbital theory predicts, He2 does not exist. Let's take a look at an He2 plus ion. So what if I remove an electron from one of those helium atoms and turn it into a helium plus ion? Well, we now have 3 electrons to put in there. So I have 2 electrons in the bonding, I have 1 in the anti-bonding, And when we calculate that for a bond order, we get 2 electrons in bonding minus 1 in the anti-bonding, so that leaves us with 1 over 2, and so we get a bond order of 1/2. Now what does that really mean? Well, it essentially means I have a bond of half strength. But this cation does exist. We can see it in certain spectrochemical analyses, but the He2 plus ion does in fact exist. It's not very strong because its bond strength is really weak. It only has like half a bond on there. But again, it's something that we observe, and it's something that molecular orbital theory predicts can in fact exist. So let's take just kind of a brief summary of where we are with the linear combination of atomic orbitals and molecular orbital theory summary. So molecular orbitals we approximate as a linear combination of atomic orbitals, and remember that means that we both add and subtract 2 orbitals to get the 2 molecular orbitals that 2 atomic orbitals can form. And so we have to get the same number of molecular orbitals out as the number of atomic orbitals we are combining. So if we're going to combine 2 atomic orbitals, I have to get 2 molecular orbitals out. Or if I'm combining 4 atomic orbitals, I've got to get 4 atomic orbitals out, or molecular orbitals out, etc. So this number of MOs out has to equal the total number of atomic orbitals that go in. Now when as I just mentioned, 2 atomic orbitals combine, we do get those 2 molecular orbitals, and there are going to be differences in energy, one of them being additive, which is our bonding molecular orbital, so it's going to be lower in energy than the 2 atomic orbitals, and one of those molecular orbitals is going to be higher in energy, and that's our anti-bonding molecular orbital, and that's higher than the 2 individual atomic orbitals. Now when we're filling in our electrons, the lowest energy molecular orbitals are filled first, and so you have our little boxes representing our molecular orbitals in our diagrams, and those are no different than the orbitals we had before, and so we can put 2 spin-paired electrons per molecular orbital, and that spin-paired just means I can have 1 spin up and 1 spin down. And so we follow Hund's rule also. If we're filling in orbitals that have the same energy, we're going to put them in singles first before they start to pair up. Now we talk about a lot of that before we start to get to the second period diatomics, because they do have some interesting characteristics once we get to those elements that have p orbitals occupied by electrons. Our first 2, however, don't do that. Now our first 2 elements in the second period are in fact metals, and we don't normally think of metals as diatomic elements. However, if we put them into the gas phase, they may form diatomic molecules in the gas phase. Now even though we're in the second period, we're actually just going to look at just the 2 s's and the 2 p's. We're going to ignore the 1s electrons, those core electrons. There's a couple reasons that we do this. One of the main reasons is core electrons are generally not involved in bonding, so we don't really need to look at them as far as our bonding diagram. But even if we did include those core electrons, what we would see is that for those core molecular orbitals, the core electrons filling the molecular orbitals, they completely fill both the bonding and the anti-bonding molecular orbitals, and those cancel out any bonding contribution that those electrons have. So you can look at it a couple of different ways. Some textbooks include all of the electrons for everything they do. Our textbook just includes the valence electrons, and that'll work just fine for us as well. So let's look at 2 of our period 2 elements, our first 2 period 2 elements, and this is lithium and beryllium. Well, let's take a look at lithium 2. Can lithium be a diatomic molecule? And we see lithium, if we look at its electron configuration, lithium has an electron configuration of 1s2, 2s1, or 1 there. And so we have that 1 electron in the 2s. So that's all we've got here in our atomic orbitals. We're going to bring those down into our molecular orbitals. So your 2s is going to combine just like your 1s and do a sigma 2s bonding and a sigma 2s anti-bonding we've got one electron in each of those two s's. There's going to come down into the sigma 2s bonding, and if we calculate a bond order for that, we would find a bond order of 1, and in fact we do see the lithium molecule, Li2 molecule, in spectroscopic studies when it's in the gas phase. Now what about beryllium? Now beryllium has 2 electrons in the 2s because it has an electron configuration of 1s2, 2s2. So it's got those 2 electrons in the 2s. So we put 2 down here, 2 up here, up there, and up there, and we end up with something very similar to helium, where we have both the bonding and the anti-bonding orbitals filled, and so as a result no bond forms between the beryllium atoms, and the beryllium-2 molecule is not a stable molecule. If we wanted to remove an electron and form a Be2 cation, Be2+, we would find that that species does in fact exist. Well, once we get past beryllium, now we're bringing in the p orbitals, and so once we hit boron, we've got to take into account any occupied p orbitals. Now p orbitals are very different from s orbitals, mainly because there's 3 of them at the same energy and they all have different orientations. So just as a reminder, those 3 p orbitals are the px, the py, and the pz, and those the x, y, and z are the axes along which they lie. Now those different orientations of the different p orbitals lead to different types of bonding interactions between the p orbitals that are on the different atoms. So let's take a look at each of those just differently. So let's look at the px's here. So the 2px in like a boron atom. So these lie along the axis. If you can imagine the 2 nuclei on the x-axis, that means that the px orbital would point at the other px orbital, and because you have the 2 lobes pointing at each other, they will have a sigma interaction that looks something like this. And so we've got our lobes right there pointing at each other, and in an additive interaction they're going to have a bonding interaction, and in a subtractive interaction they're going to be anti-bonding, and we get that node there. Okay, so we've got a bonding and an anti-bonding. So we call this sigma 2p and sigma 2p star. Okay, so lots of different ways of expressing those. But we've got we had our sigma 1s star. We had our sigma 2s star. Now we've got our sigma 2p and our sigma 2p star. Now the one thing that we haven't seen yet are any pi interactions here. We do have those with the 2py and the 2pz. So these orbitals lie side by side with each other, and as a result they're going to have a pi interaction. Now the interesting thing with that pi interaction is sometimes it's higher than the sigma interaction and sometimes it's lower. And it turns out because we're looking at molecular orbitals and we're delocalizing all of our electrons across all the different orbitals, there gets to be a mixing in that sigma interaction between the s orbital and the px orbitals, and the higher the amount of mixing, the higher energy that particular sigma molecular orbital is going to be. But let's take a look at the 2py and the 2px for right now. And so we do have 2 kinds of mixing. So we can see we've got the 2pz on one atom over here, and I'll just put in a little b so you can imagine one of my boron atoms here, one of my boron atoms here, and we have interactions between the lobes there. So if it's an additive interaction, well, that's going to give us our bonding orbitals there, and so you can see we have the 2 lobes supporting each other above and below the plane of the atoms. And then we've got our anti-bonding up here, and essentially what that does is it subtracts out any of the area between them, or the region between those lobes, and they actually end up at with different phase. There's lots of different ways you can look at that, but we do have a node between the atoms there, and so that's our anti-bonding. We get the exact same thing here with our 2py orbitals. Again, you have you can imagine boron there and boron there, and so you get bonding in a different plane and anti-bonding in a different plane. Now we mentioned this 2s, 2px mixing, and this is really important before we look at the order of how everything goes. if we look at how the order of orbitals go by energy, what we see for boron, carbon, and nitrogen is once we hit the sigma 2s, so that bonds nicely here. We've got our sigma 2s star here, but you do get some s and p mixing of the atomic orbitals for this sigma 2p in boron, carbon, and nitrogen. And so as a result, the sigma 2p is higher in energy than the pi 2p. Once you get to oxygen, fluorine, and neon, well, that changes, and your pi bond is actually higher in energy than your sigma 2p bond. And so we get this switch in here. Okay, so it's just something to keep in mind. So boron, carbon, nitrogen, you get a significant amount of s and p mixing for that sigma orbital, and that raises the energy of that sigma orbital. The oxygen, fluorine, and neon doesn't have as much mixing of the s and px orbitals there, and that keeps the sigma 2p energy quite a bit lower, and it lowers it below the pi bond. So what effect does that have in the ordering of our molecular orbitals? Well, when we're looking at a molecular orbital diagram for our boron, carbon, and nitrogen here, our two s's here still just form a sigma 2s and a sigma 2s star. When the p's mix, okay, I'm mixing in 6 total atomic orbitals because I've got 3 p's on each atom. And so they fill in the order of a pi between the 2 p's first, and there's 2 different pi interactions there, the py and the pz. I can have a sigma 2p here, that's with the 2px. And then we have our anti-bonding, pi 2p star, and then we have our sigma star up here. Okay, so again, they're always going to fill in order of energy, and here we see energy going up from the bottom. And then if we look at oxygen, fluorine, and neon here, everything kind of goes in the order we might expect. We have our sigma down here, pi 2p star, and then sigma star 2p. And so all of those go up there. So the only real way to get these orders is to memorize them. There's no easy way to figure out what they are. One thing we can do with those orbital diagrams is to figure out, is a diatomic molecule diamagnetic or paramagnetic? Well, let's take a look at those 6 diatomic molecules, boron, carbon, nitrogen, oxygen, fluorine, and neon. And we see that for boron, we fill in those 2 electrons into the 2p. We've got 6 total valence electrons for B2 because the boron has 3. And so I fill in 2 here, and then according to Hund's rule, I got to put in the 1 there and the 1 there, and I should see that boron is in fact paramagnetic. If I did a bond order calculation, I would find I have 2 electrons in a bonding orbital. I have no electrons, or actually we can use the sigma 2s's as well. I have 4 electrons in bonding orbitals, 2 electrons in anti-bonding orbitals, so I have 4 minus 2 over 2, and that would give me 1, and I would see a single bond between borons. If I look at carbon, now I have 4 electrons each, so I have a total of 8. So 2 go in here, 2 go in here. The next 4 all go into the pi 2p, and if I do a bond order calculation, I see that I've got 2, 4, 6 in bonding orbitals. I've got 2 in anti-bonding, so I have 6 minus 2 over 2. That gives me a bond order of 2. So I have a higher bond order in carbon than I do in boron. And look at this, I actually have a shorter bond length because of that higher bond order. I also have a higher bond strength, a higher bond energy than I do in boron. And then when we get to nitrogen, when we did the dot structure for nitrogen, we saw that we had a triple bond. Let's see if that's what we get for molecular orbital theory. I've got 10 total electrons I got to put in. So I've got 2, 4, 6, 8, 10. I've got 2, 4, 6, 8 total electrons in bonding orbitals. I've got 2 in an anti-bonding, so I have 8 minus 2 over 2, so that's 6 over 2, and that's 3, and that in fact is the bond order for nitrogen. That's what I would expect from the dot structure as well. Once again, I have an even shorter bond now that I've gone up another bond order, and my bond energy is even higher. Now we go over to oxygen, fluorine, and neon, and we can see that we're filling the sigma 2p now before the pi 2p bonding orbital, and I'm starting to put some electrons into the pi 2p star. We also want to look at whether something's paramagnetic or diamagnetic. I see here in my boron I've got 2 unpaired electrons, so that should be paramagnetic. In both my carbon and nitrogen I actually have all paired electrons, so those would be diamagnetic. For oxygen, I see that oxygen is paramagnetic, and so we saw on our very first diagram for this chapter, the picture on that slide had liquid oxygen being poured between 2 magnets and actually sticking there, and this is why oxygen is considered to be paramagnetic. If we calculate a bond order, we should get 2 based on what we see for a dot structure. I've got 2, 4, 6, 8 electrons in bonding orbitals. I've got 2, 4 electrons in antibonding orbitals, so I have 8 minus 4 over 2, so that's 4 over 2, so I get a bond order of 2, and that's what I see for a dot structure as well. Okay, and we go on to fluorine. We see that fluorine is diamagnetic, bond order of 1, and for neon we filled up all of these orbitals, and I end up with a bond order of 0, so I have no bond length or bond energy there. Now we can move on to heteronuclear diatomics, so as opposed to homonuclear diatomics. So heteronuclear diatomic is where you have your 2 atoms are different, and this is quite a bit more complicated situation, mainly because your orbitals here are of different energies, and your interactions can really vary depending on where the orbitals end up in terms of energy, and also the symmetry of the orbitals has to be taken into account as well. And so we can take a look at something like NO here, which is actually an odd electron species here. We see that the nitrogen orbitals are just slightly higher in energy than the oxygen orbitals, and this is because oxygen is more electronegative, and so it's the energy of its atomic orbitals are just slightly lower, and that has a little bit of an effect on how the diagram is drawn, but not a whole lot. Not much is different there than if we were to do N2 or O2 as far as the ordering of the orbitals. But if we look at something that's kind of crazy like HF, we see that the energy of the 1s orbital in hydrogen is actually higher even than the 2 p's in fluorine. Of course, fluorine's got the 2 s's and the 1s, even lower in energy. Fluorine's very electronegative. It really drops the energies of those atomic orbitals. But what we end up with for HF is a sigma overlap between the 2px and the 1s orbital, and once hydrogen has made that interaction, that's the only orbital it has left to do anything, and we end up with a couple of atomic orbitals left over here. They did not turn into molecular orbitals because they weren't able to be combined with the hydrogen there. So lots of different things going on there. We're not going to do a whole lot with the heteronuclear atomic orbitals. The important thing to know is that their molecular orbital diagrams are much more complicated. And last thing we're going to take a look at is polyatomic molecules, and these are really complicated systems. Generally, you're only going to calculate any kind of molecular orbitals using computers or workstations, some pretty powerful calculations. We can look at a comparison of how we do some different molecules here. We can look at the Lewis structure here for ozone, O3, and we would draw it something like this, where we have a bond in resonance going back and forth, a double bond and a single bond. And if we do the valence bond model, we see we could draw the pi bond here. If we'd wanted to, we could have drawn it here, or between those 2 atoms there. it doesn't really matter. If we go on to molecular orbital theory, what we find is that these orbitals are in fact delocalized across all three atoms here, and we would have different versions of that molecular orbital as we go up in energy, but this would be the lowest energy one. And we can go to an even more complex structure here. We look at the benzene structure, and this confounded people for quite some time because we see that we have 3 double bonds in benzene and 3 single bonds in benzene, and then it goes through its resonance here, and the double bonds and single bonds change places, and what we find is that all of these bonds are exactly the same, and molecular orbital theory helps describe that a little bit better, to where we've got our lowest energy orbital shows just a bunch of delocalized p orbitals here, all bonded together into a single molecular orbital. So that material is quite a bit more complex than we want to get into right now. If you have to go into organic, you will talk about that delocalized ring system that benzene has that plays quite a role in organic chemistry. Well, that's all we've got for Lecture 20. It's a lot of material. Some of it's pretty difficult. So as always, if you have any questions, make sure you contact us.